Welcome to this video from Derby Physics Tuition, and this is a great question from OCR about the kinetic theory of gases and really testing your understanding of that subject area. So let's have a look at the question. So there is a lot of helium in the universe. This was also true of the Earth when it was formed billions of years ago. However, only small traces of helium are now found in the atmosphere of the Earth. Use the kinetic theory of gases to explain why only small amounts of helium are found in the Earth's atmosphere. Use the information below to do suitable calculations to support your answer. So they've given some data here: the temperature of the Earth, atmospheric temperature, the mass of the helium atom, and the escape velocity from Earth, which is 11 kilometers per second. So they're sort of giving you a clue there as to what equations might be relevant when answering this question. So how do we answer it then? So we've got our question there, and the first point, this is a 6-mark question, so they're actually looking for 6 individual points, including the calculation. Now, at a certain temperature, all atoms have the same average kinetic energy. So in a gas, at a certain temperature, all atoms have the same average kinetic energy, and we could say that helium behaves like an ideal gas, and the kinetic energy of the helium molecules can be calculated using the equation. Kinetic energy is 3 kT over 2, where K is the Boltzmann constant and T is the temperature in Kelvin. So let's use that equation to calculate the speed of the molecules. So what would our calculation be using that equation? Well, the temperature is 10 degrees, and converting that to Kelvin is 283 Kelvin. And this equation here is telling us that the kinetic energy of a gas molecule is equal to 3 kT over 2. So we can say that the kinetic energy, use the kinetic energy equation, and that term there is the mean of the square of the speeds. So we've got our kinetic energy term, and it equals 3 over 2 kT. And if we rearrange that, the root mean square speed is equal to root 3 kT over m. So the 2's have cancelled out, and I've just rearranged that. And so the root mean square speed comes out as 1.3 kilometers per second. So basically what the calculation is showing there is that I suppose to simplify it, it's the average or the mean speed, the root mean square speed is 1.3, but the escape velocity is 11. Now this root mean square speed is a lot lower than the escape velocity, the velocity required to escape from Earth. So how do the molecules, how have the molecules of helium escaped from our atmosphere? So how do we explain that the Earth only has small traces of helium in the atmosphere when the root mean square speed is 1.3 kilometers per second and the escape velocity required for these particles to completely escape from Earth is 11 kilometers per second? Well, we can explain that by saying that the atoms have a range of speeds modelled by the Maxwell-Boltzmann distribution curve, and that's what a typical Maxwell-Boltzmann distribution curve looks like. it's got the speed of the molecules on the x-axis and the number of molecules on the y-axis. And this point here represents the most probable speed that the particles will have. And the root mean square speed is somewhere around this region here, which is 1.3 kilometers per second at 283 Kelvin. So 11 kilometers per second will be somewhere over here. Okay, 11 kilometers per second, which is the escape velocity. And so how do the particles actually achieve that speed? So what would happen is that particles with the speeds in this region here would collide with each other, and there would be a transfer of kinetic energy. So some of the particles would gain more energy and therefore greater speed, and they would eventually gain enough energy to have a speed greater than the escape velocity, which is 11 kilometers per second. So even though most of the particles have got a speed of less than 11, by colliding with each other and getting lucky, I suppose is an expression you could use, by colliding with each other there'll be a transfer of kinetic energy from one particle to another, and they would eventually gain a speed greater than 11 kilometers per second. So even though the root mean square speed is a lot less than the escape velocity, by colliding with each other they would eventually gain that speed, and that would take some time for that to happen. But it's a similar idea for why puddles disappear even on a cold day. The molecules of water within the puddle collide with each other, transfer energy, and eventually they gain enough energy for evaporation. And this sort of thing can be modelled by the Maxwell-Boltzmann distribution curve. Okay, and so the next point is that the faster atoms will have escaped the Earth over a long period of time. So again, by colliding with each other, these particles gain that speed, become faster by collision. And the final point you could have mentioned was also recognition of the fact that the Earth was significantly hotter in the past. So we used 283 Kelvin or 10 degrees centigrade, but in the past, when the Earth was first formed, the temperature was a lot higher. So really interesting question there about the kinetic theory of gases. Quite a challenging one, but it really does test your understanding of this particular area of thermal physics. And if you do have any questions or comments, please leave them in the section below, and thank you very much.